We present 360-degree volumetric portrait avatar, a novel method for reconstructing photorealistic and animatable 360-degree portrait avatars based on monocular RGB inputs. Digital human avatars find a variety of applications in the AR/VR, gaming, and entertainment industry. However, creation of digital avatars for such applications takes place in modern studios using complicated and expensive capture setups, thereby making it inaccessible for common usage. Thus, there is a need for reconstructing personalized avatars with little data using ubiquitous sensors such as a webcam or a smartphone camera. Current state-of-the-art monocular avatar reconstruction methods employ 3D morphable model-based face trackers which fail to capture the side and back views, resulting in front-facing incomplete avatars. We thereby propose 3VP avatar which takes as input a monocular RGB sequence comprising of a static 360-degree recording of the human subject followed by a dynamic sequence capturing various expressions. Our method leverages the static sequence to obtain the geometry and associated texture, which is laterwards used to track the dynamic part of the sequence. We use the track geometry and the static camera poses to reconstruct an animatable avatar by learning the 3D radiance field based on volumetric rendering. Our method pipeline comprises of two stages: template-based tracking and the volumetric deformation and appearance modeling component. The first component is the template-based tracking. Given the static frames, we initially run a structure from motion approach to obtain the camera poses along with a 360-degree textured template mesh. The resulting mesh is then rigged to a 3D morphable model, here the SimpleX model, through registration followed by transfer of LBS weights from the SimpleX model to the template mesh vertices. The rigged template can now be deformed using SimpleX pose and expression parameters and subsequently used to track the dynamic frames. We optimized for the SimpleX parameters on a per frame basis by using a differentiable rasterizer for minimizing a photometric loss based energy function. After obtaining the tracked SimpleX and deformable template meshes, we now turn over to the second component of our pipeline, namely the volumetric appearance representation component. We model the deformation as well as the appearance of our avatar via a neural volumetric representation. We initially model the coarse deformation field by computing a deformation gradient between the deformed and canonical SimpleX meshes. We sample our rays in the deformed space and estimate the nearest neighbor triangle for each point and deform the sample point xt to the canonical space point x based on deformation gradient of the nearest neighbor triangle. The resulting canonical point, however, cannot model fine deformations like expressions, so we introduce displacement bend fields in the form of volumetric feature grids corresponding to different expression states. These feature grids are queried individually by the deformation network, outputting different displacements, which are then linearly combined to produce a final displacement dx, which is then offset to the canonical point x. The resulting location is then queried by the appearance network A to output the density and color corresponding to that point. These values are subsequently combined for all points along the ray using volumetric rendering to produce the final image. We compare our method against state-of-the-art monocular techniques, namely FLAIR, point avatar, and Insta. Since Insta is a head-only based method, we therefore ignore the torso region in this case. We only show the comparison for the frontal view since the baseline methods are mostly front-facing. Our method produces sharper results than the competing methods. particularly in the torso region as well as hair region. It produces meaningful mouth interior, in particular, better than flare and point avatar, since those methods do not model the mouth interior additionally. Our method also provides a stable and smoother tracking than the competing methods. We show some ablation results, namely the blending of appearances instead of deformations, followed by the direct conditioning of jaw pose and expression parameters on the appearance MLP, and finally the removal of the personalized blend field components on top of the coarse deformation field. We can clearly observe that the quality of the mouth interior is better in our case. Finally, we show our 360-degree avatars under novel views and expressions. Thank you for watching.